So welcome once again. Today's topic is very interesting for everyone since we will discuss four very valuable information about how applying HPC, AI, and some other technologies into the agriculture sector. So with us, we have four expert speakers. I will introduce each one during their presentation. And with you, I'm Tina Mark from Arctur, and will moderate this meeting. Okay. So before we are heading into our presentations, just a brief introduction to EuroCC and National Competence Centers for everyone who's not familiar with this entity. Actually, is the NCCs have been established during the EuroCC1 project and are established in 32 European countries with the mission to contribute to HPC knowledge, to HPC infrastructure, and to connect industry, academy, and public institutions with the aim to grow the knowledge and services that are embracing HPC as such, so supercomputing and artificial intelligence. And one of the national competence centers is also NCC's link. We are located in Slovenia, and 5 partners in the consortium. And we are thrilled that you are today with us. And I would suggest just start with our first speaker. So today with us, let me introduce Stevan Čakić. Stevan, if you're ready, you can start your presentation. And meanwhile, just a few words about Stevan. So he's a researcher and teaching assistant at the University of Donja Gorica from Montenegro. And he is actually dedicated in computer science, specializing in computer vision and machine learning, and applying advanced technologies such AI and IoT for development of smart agriculture systems. And today we will have a chance to learn more about their innovative project where they actually prepared a nice system, so apply machine learning and IoT devices for next generation hen farms. So Stevan, you can start.
So, hi everyone. I hope you can hear me well and also you can see the presentation, right? Okay, great. Thank you, Tina, for presenting me. Today I will talk about some platform related to AI, how we used AI and Internet of Things with HPC to develop, I would say, very interesting use case, how we can use AI and HPC to create one algorithm for chicken monitoring on closed farms. So why we done that? And I would say I would like to say also that we also work now on this project to create better results and all of these things. But firstly, I would like to define the maybe not the problem, maybe more the questions related to farming sector, poultry farming sector, and how you can use, for example, AI in this specific sector. So first problem we try to resolve by these technologies, how we can use AI and HPC to address the growing demand for food and animal protein, because we know that demand for the food, especially for chickens, are very high, and how we can use AI to create not just to create more benefits for farmers, but also for these chickens, and this is also one of the things, very important things in this project. The second thing is how do we scale and optimize animal farming process to answer the needs of the global meat market. Also, not just local meat market, but also the global meat market, because we focus our project more on global view, how farms on different countries can use this approach to help with AI and HPC to develop very useful system. And can we use advanced AI models to contribute in optimization of poultry farming? So the main focus of this project and research, we divided this in a couple of challenges. First challenge is how we can stop or how we can stop disease outbreaks among chickens on farms. How we can detect dead chickens and remove them easily. And also we need to be careful about all basic life needs of the chickens on the farms, like feed, water, lighting, air conditions, and all of these things. And also sanitation and cleaning, as I mentioned already before. So, okay, this is really important, but how we can do these things together and to ensure animal well-being and make the life for farmers easier. This is the main focus. So some of the goals, maybe this is more like technical thing on the project, but create camera sensors based on deep learning and IoT edge devices, or how we can integrate well enough or fast enough and accurate enough model on a small edge IoT device and connect this device with camera to monitor farm all things, movement, for example, of the chickens that I mentioned, and some of the other things. Also, very important thing here I would like to mention, and this is HPC support during the development phase. How we used HPC to create these solutions for the farms based on edge AI, computer vision models, and process. We use, of course, HPC for a fast model development and doing a lot of experiments during the phase of development. And also, this is enabling deployment on edge device. This is very important phase, because it's not enough to have enough inaccuracy, because we need to create a system that is very fast in predictions. And if you have a small edge device, this is not that easy, because these devices don't have enough computer power to do these complex things very fast. So we need to create this trade-off between model accuracy, and prediction time. Project key tasks. We divided this in at least two main tasks. One is object detection. And why is this so important? Or chicken detection in this specific case, because we need object detection for counting chickens on the farm. This is really important because with that we can predict, or we can analyze density between the chickens. And we use also object detection for detection of dead chickens by analyzing different frames in a row and analyzing the movement between these frames on the video. Other important task is object segmentation. We used object segmentation for estimating of the weight of the chickens on the farm. So with object detection, it's not enough because in object detection task, you have just rectangles around the chicken and you catch or collect the part of the image that is not the chicken, and it's really hard to predict weight with object detection. And we use also, of course, object segmentation process to try to estimate the weight of the chickens. We used also automatic machine learning procedure to analyze, to find best parameters for our AI models. So this is implementation phases of the project. Firstly, we have this design part where we defined requirements for the project, like functional and non-functional requirements, and also designing experiments. The second part is a learning or learn part for development of prediction models using HPC. I mean, computer vision models that I mentioned before for object detection and object segmentation. And the third part is very important because this is like the most practical part, because it is integration between edge AI devices and these AI models we developed in the previous phase. Of course, we had during the whole project a verification and validation phase on directly on the farms, and project management, dissemination, and exploitation of the project. So this is simplified, of course, a really simplified architecture. We used for this project, we used two different farms here in Montenegro, one called Radinović and other Franca. We collected data from these farms, stored it on specific some store data storage. Also, of course, we used these edge JetSon device to collect data, and use different tools to annotate data and to create models. We used HPC system provided by IoT Advanced Computing from Croatia, and we used faster CNN and mask CNN model architectures in the first phase of the project. And after we used different models like YOLO V8, YOLO V9, and all of these things. This is from the research paper published last year on MDPI. This is how we organized the development phase. We had the two different phases. First is like something we called offline loop. We used offline loop for model development, and this offline loop contains like model creation using HPC, data set storage, and we on the other side we have online loop. We use online loop to test our model. This is related to more with AI edge AI sensors for prediction in real time. Okay, about data creation, this is maybe not that important, but we collected 4,000 images annotated manually, because in that time we didn't have like now semi-automatic annotation, because now it's much easier for annotating objects on the images. And with data segmentation, object segmentation, we had 1,000 images, and we use, of course, data augmentation process to extend our data set for a video RoboFlow tool. So this is like the process. This is one of 4,000 images for object detection. And imagine 2 years ago or 3 years ago when we done this to manually create these rectangles around the chickens for 4,000 images. This is for segmentation. Also manually we had annotated 1,000 images. But as I mentioned, now with this RoboFlow tool, you just upload a couple of images, use default Dino model, and this model helps a lot now with the annotating different classes on or doing object detection, but with firstly with annotation with this model. You just put your data, select this specific model, and put the confidence threshold, and you have for example, you need. I tested this. I need, for example, for 50 images, 5 minutes for annotation, because after automatic annotation, I need to check, I need to review how good was that with annotation. Of course, you can use your trained model to annotate new images, for example. This is another solution. And this is very interesting because you can see in this image, generated image. This is not the image from the farm. So what I would like to say here, because now with generative AI improvements in the last couple of years, we can generate new images not by collecting these images and putting cameras on farms, but just use a couple of images from the farm, put it in the generative AI model, just do some fine tuning, and after that you can create new images just by calling these algorithms to generate new images. And I would like to mention again, this is generated image. This is not the image, real image from the farm. But I think this is really hard to say, is it real or not? So okay, we trained tested different models, and we used HPC. We trained our model on multiple GPUs to train it as far as possible. I mean, with more GPUs in general, it's not always, but in general, at least you increase the training time for your models. So main outcomes, we annotated large amount of data. I mentioned how much. Or of course, we had some already annotated data set from DunavNet, and we extended this data set with more images, because in general, with more data, you improve the performance of the model. Of course, with HPC and the different experiments, we selected the best, or we thought, but it improves during the time, best parameters for the trade-off between prediction time and accuracy. Of course, we integrated this model on edge IoT device. And as you can see on this image, we integrated our models directly on a platform, web platform, Agronet. And you can see some results directly here. This is like all the dates, but it's almost the same now. But with better precision results, especially for weight estimation. Okay. This is for the weight estimation. This is directly from one farm. This is, as you can see, from the last year, but we have some new data, of course, because this is live system. It's not just prototype. It's also integration with a real situation on the real farm. This example is from one of the farms in Canada. And as you can see, these percentages mean the density of the chickens on a specific frame. As you can see, this is not that precise for some cases because AI is always some probability, but now we are trying to improve these things. So some of the business benefits, as you can maybe you already can know, but improved AI platforms in general for a smart agriculture, time saving creation of AI predictive models. HPC is a very important service or platform for developing these projects or models. Focus on early disease detection, because this is the point, this is the whole point, how we can detect on time maybe unhealthy chicken or dead chicken to prevent disease spread on the farm. Of course, improve. It's easier for farmers to monitor farms. So this is some of the benefits for the business, and this is for the conclusion. As you can see, deep learning can help a lot to the users, in this case farmers, to improve existing poultry farm management solution. I mentioned this a couple of times, but sometimes the best model performance is not enough. We need to check model size and prediction time. Also, it is possible to integrate good enough deep learning model with a small edge device. HPC can help us by a lot on development, especially in the phase of development. But also we need to always be careful about the bad things, like effects on the environment. And I think that's it. I just want to mention that this is the project developed with, especially in DigitalSmart company, with collaboration TunaNet company from Serbia, University of Donja Gorica, and 2 farms from Montenegro, Žetinović, and France. And this is the slide for that. So thank you for listening.
So let's go ahead with presenting our next speaker. So I would like to say a nice hello to Mr. Tomaž Bokan, who is a senior international technical expert from the ITC Murska Sobota and has over 20 years of experience managing R&D projects, pilot implementation, technology transfer, and project commercialization. And he also has a very good skills level for leading the international commercial projects, especially with implementing the technologies such as IoT, blockchain, and robotics. And today in his presentation, he will highlight how AI-driven innovations are transforming precision farming, food processing, and supply chain optimization, and as he said, enhancing both efficiency and sustainability. So, Tomaž, if you're ready, let's start.
Yes, Tina, thank you very much for the introduction and invitation to this event. I hope you can see my screen. Yes. I first have to say that it was very nice to see this presentation from Stevan, because actually we participated in one of the projects where some early stage of this was developed without the cameras, but it's very nice to see the progress through the years. So I would like you present today actually how we use some technologies in our domain. So actually it is not so much technical presentation as it was maybe the previous one, but the reason is that we are a non-profit organization. We are from Murska Sobota, and actually our focus is somehow on promoting and bringing new technologies into the region, but also wider to the Slovenia and this part of the Europe. So we are actually involved in different initiatives where we deal with these technologies, from Earth observation, blockchain, also economics on the farm and so on. And we are also one of the EDIH members. So as we all know, why technology is very important in this agricultural sector. There was already some examples presented, but I will focus now more on these arable crops where we are mostly active. So there actually is already expectation that our yields of cereals will remain stable if we will use the technology, meaning precision farming, soil health measures, and so on. And this is also something what is identified in this European agricultural outlook. So we see that technology is very important, and that everybody is counting on our work, I would say, to implement the technology into all parts of the food production also. So let me first present you one of these three projects, which I will briefly go through to show what we do and how we use AI and HPC. So first of the project, it's Green.ai. It's energy efficient AI data spaces. As we know, we need new data that will be used and harnessed to somehow transform this to useful stuff to actually support the green transition and business and societal challenges. So in this project, we are actually not tackling just the technological part. We are focusing also on user satisfaction, on efficiency on the farms, and then this, of course, leads to optimized use of resources, soil health, and so on. So on the next slide, which you see now, actually, I would present you what is current experience, for example, on field of precision agriculture. So if we see now these four pictures starting on the top left, so we see that farmers are using basic approaches for precision fertilization, for example. So there is a picture from the satellite where we can see these NDVI images, and then the tool is transforming this to some zones which have common values. So those zones are assumed that they need the same level of fertilizer applied, and this is then transformed into a machine which is then used on the field to actually apply the fertilizer, or potentially it could also spray the field with required quantity. And this is a standard approach which is used currently. There's no AI or no deep learning or whatever used in this approach. But what is the main challenge is that actually this process is quite time consuming. It requires some field work, and it requires also some experience. Namely, we have a tool which needs to be fed with different data. Like, for example, the tool doesn't know how much fertilizer should be applied on some point. The tool can actually extract different areas of a field, but the tool itself doesn't know how much gram of the fertilizer should be applied. This is something what currently is done by sampling the field plant or soil, and then the expert decides the quantity of fertilizer which is needed for each particular zone. So this has to be entered before the machine can go on the field. And as we understand, in the case of a high number of fields, this is quite time consuming and requires a lot of work. So this is something what we would like to optimize by using AI and big data approaches. Then the second scenario which we are targeting is optimization of harvesting time. Here we can see four pictures starting from the top left with 3 days or 2 days difference, where we can see actually how dry was the product on the field so that it is appropriate to be harvested or not. Why is this important? Actually, the similar case as I mentioned before. For example, a farmer has 20, 30, 40 fields which need to be harvested. Especially in some countries in Europe, the fields are not very, very big, and they can also be on a slightly different locations. So the sequence of harvesting, it's very important. So the farmer needs to know in which order he should start the harvest, not to actually go to a field which is not so ready and then to continue on the next field which is more ready. So to have more homogeneous product, this is very important to analyze all the data from the satellite images, but also combine with environmental data to actually predict the optimal harvesting sequence. Then the third scenario, which we are dealing with in this use case, it's slightly similar to this what was presented already before. So we are detecting plant pests and diseases. This is actually very important because in case of larger fields, it is very difficult to spot some areas which have irregularities or if some pests would occur on some specific parts of the field. That's why by analyzing the satellite images, the areas can be identified, and this system based on learned database of previous cultures and images can identify areas which are potentially affected. So then the action would be that either the farmer can go there and take a physical look of the plant or the parcel, or potentially also a dedicated drone could be applied to make more specific or more detailed pictures of that particular area. And then, of course, the action is that then they can apply the fertilizer or the pesticide maybe on that particular area if needed, not to spread this disease. Yes, so a little bit about the technical and data dimension. So what we are using here, actually, I have to say that since we are not the developer, we are somehow more close to interact with the farmers, and on the business part of this, we are developing some parts of the solution, but our main partner here is from University of Maribor, the Gamma Laboratory for Geospatial Modeling with Professor Mongus. And actually what is used here is this different end-to-end solutions for generating the maps, including feature learning and classification algorithms and so on. And then these three use cases, what is happening at the end, we have a My Farm dashboard, which is dashboard used by farming advisors and farmers. Actually here our closest partner is Kmetijsko-Gozdarski Zavod Murska Sobota. It's a farming advisory service. And inside this tool, we are now experimenting in this project to provide targeted fertilization suggestions based on AI, then also these harvesting sequence suggestions and pest and disease detection as described in the previous three scenarios. Then the second project which we somehow work on and is involved with farmers and agriculture area is more on economic side of the production. So we are here focusing on milk and pork production on farms, but also on carbon footprint of those farms and so on. And actually here the challenge is that economic data of the farm is collected mainly manually or in different reporting systems and so on. And if farmers would like to compare this to actually see how good they are compared to some other farms, or to identify areas what they would like to improve, this is not so easy if the data is not collected and it cannot be easily analyzed. So this project is actually focusing on demonstrating the value of this data to boost the economy. But what does this mean in reality? You can see one example here. So we have a dashboard for the farmers where they either enter part of the economic data of their farm, or some data is also received from other existing data sources. And then in this example, you can see how we use the AI algorithms to suggest optimized scenarios. So if you imagine that we have one farm which has, I don't know, 30 animals and they produce this quantity of milk, and some other farm has 50 animals and produce some other quantity of milk, and so on. Then, of course, there are some options that if you have a lot of data from different farmers, you could suggest, okay, you have some option to improve on this field, and then the farmer can actually analyze this more deeply with also help of farming advisor, to actually find why he has some areas which are somehow underperforming, or if he has some areas which are overperforming. And then based on this, he can also simulate the scenario. So if he would, for example, improve the quantity of animals, or if he would improve some other parameter, how this would reflect, or how this would reflect his production based on other examples which were already existing. Okay, and then the third project which we are somehow dealing with artificial intelligence, it's called Brain. It's one of the projects which is co-financed by Interreg Danube Region Program. And the goal here is to increase competitiveness of SMEs and also familiarize them with the relevance of artificial intelligence and technologies which are used. In this project, we somehow deal with concrete technologies, and our demo case is on the field of agriculture, on the production of vegetables. So we will implement 3 activities. So first is use of unmanned Earth observation vehicles and capture the data from the terrain. Then we will implement a robot for spotting and removing weeds, and integrate AI solutions into this to actually make additional use of this data which we can gather in this demo case. So the concrete steps here are to actually use drones for capturing NDVI images, and to train the vision models to actually identify the areas which may have some irregularities, but also to track the crop health as such, and to make yield prediction and other potentially useful data for the farmer. Here we have a more closer look. We have one field which we are working this experiment on, and here on the right side you can see one example where there is some I think it's paprika on the field, where we actually started to use some algorithms to track the number of plants and also to monitor the growth. Actually, we are here quite in an early phase, so I'm sure some other solutions which will be presented today are much further, but this is the practical use in our case. Yeah, here we have one more example, which is maybe not so, it's one big field, and then you can see the details on this picture. It's different cultures. I think it's pumpkins and paprika on the same picture. And then the robotic technologies, which I mentioned before. So we have a robotic platform which is capable to remove weed and also to perform spraying in vegetable production. We say it's AI powered because our goal is to actually, based on all the data which we have from the field, from the IoT data, and also from the drones, to actually have models which will then be input into this robot. So the actual spraying could be done based on actual plant location, but also to actually define the periodic sequences or the duration in which the robot has to go out on the field and to perform some work, so that we can know, that we estimate when the growth of this unwanted plants will be highest. So to actually do all of this stuff I mentioned, we have IoT equipment installed, which is basically solar powered gateway for LoRaWAN. Then we are measuring the air temperature, humidity, rain quantity, leaf wetness, and so on. And all of this data is fed into our data space infrastructure, which actually is very important and is somehow the key of our solutions, because to actually do high power computing and to deal with big data, it is very important that the collection and sharing of data is also done on a way which is fair to all involved parties. So we have this data space infrastructure, which is actually already up and running, and we are actually using a governance model. We comply also with European standards defined by IDSA, and this is the basis for all of our projects, which are somehow dealing with farmers and also with universities to actually exchange information and to do the modeling and so on. So this is actually from my side the overview of what we do. So I hope I was in time and we have some minute for questions if there.
Let's say hello to Mr. Federico Battini, an energy engineer with a PhD in urban and building energy modeling. And he's working as a data scientist as IFAB, where he focuses on projects related to weather, climate, and energy, applying advanced data analytics to drive innovation in the specific fields. So today he will outline the development of weather classifier that, given two numerical weather prediction models, is able to select the most accurate model for each grid cell and forecast time setup, thus improving forecast quality with limited effort. So Federico,
thank you, Tina.
Go ahead.
Thank you very much for the introduction. I hope you can hear me well and also see my screen. So thank you. As you said, my name is Federico Battini and I work as data scientist at IFAB Foundation. My presentation is going to be a little bit of a merge of the previous two. So I will go through a couple of projects focusing both on agriculture and weather forecast. Indeed, we are going to talk about the main output of one of our projects, which is an improved weather forecast that we were able to achieve with a limited effort by using a classifier-based approach. So first of all, a little bit of an introduction about what IFAB is. So IFAB is a private foundation. We have more than 35 members and we are located in Bologna, Italy. And we focus on projects that are enabled by big data, AI, HPC, and quantum. We have several projects that we are working on and we like to divide them in topics, let's say. So we have a project in the health department, also on digital society, earth and climate, among which you can find some projects related to the agricultural sector and also project about manufacturing and tech. If you sum these numbers up, you get 6 projects that we do with about 85 different institutions. Of these 46 projects, 27 are directly funded by IFAB through open and member-served course. And there are 16 projects that we develop ourselves alongside with our members and the National Center on High Performance Computing, Big Data and Quantum, which is located also in Bologna. We also develop projects for small, medium enterprises, and so far we developed 3 of them. But going to the project that I'm going to introduce today, the first one is Sustain, Digital Twin for Precision Agriculture. This project started in the latest months, so I will briefly outline the project, what we are going to do, focusing on one of the areas on the project, and then I will move to another one for which we already have some results dealing with weather forecast. This is really important also for agricultural applications. So about Sustain, here we want to develop and test an agricultural digital twin. This is designed to support small, medium enterprises of the sector in order to make them able to simulate and model dynamic system in order to accelerate their digitalization. So we have 4 areas of work. The first one involves generative and edge AI. In the second one, instead, we are going to develop the digital twin architecture for agriculture. And in the third area, we're going to use this in order to improve crop resilience. And we also have another area of work in which we want to try to apply federated learning in agriculture. So these are the partners of the project. As you can see, these are mainly academic institutions, even though we have also some industrial partners. The industrial partners are involved also with us, of course, in the first hour of work about generative and edge AI, in which I'm going to go a little bit more in detail now. But before talking about this, since I've been told that this presentation is for a broader audience, I would like to introduce a little bit what one of the algorithms that is usually employed for generative AI is and how it works. So this is a generative adversarial network. So what it is, they are also called GANs, which are a type of deep learning algorithm that is used for generating new data that are similar to a dataset that is provided in training. Of course, GANs are not that popular for agriculture, but they are well known for face generation. These 6 faces that you can see in the slide are all fake. So none of these people actually exist. And there is a website which is called thispersondoesnotexist.com that you can go to. And by refreshing the page, you will see a face that is generated by AI and associated to a person that actually does not exist. So the principle of operation is that we have 2 neural networks. One is generating images and another one is, let's say, saying whether these images are true or fake. So you have this competition between one network that wants to fool the other. And so from this, you get the part of the name, which is adversarial. So you have basically a generator and a discriminator. You can see the generator as a thief and the discriminator as a police officer. The thief wants to fool the police officer in believing that what it is providing is actually true and not fake. So at the beginning of the training, the generator does not have actually anything it has to generate. So you will get some images that do not really make sense. So it will be easier for the discriminator or the police officer to say that as the training goes on, the discriminator is providing some feedback to the generator, and so it will be able to improve the image generation until you get to a point in which the discriminator will not be able to tell whether these images are true or fake. The generator, of course, is able to generate images that are different one from the other and that are not only the same image. This is due to an input noise vector, which is a vector of random numbers. I'm saying this because it is important for a part of the project. So about the project, in this part of the project, we want to develop an edge AI device that is going to be installed on agricultural machinery in order to support real-time precision agriculture. So we want to start from an input image that you can see, for example, in the slide of grapes in vineyards. And starting from these images, we want to use GANs to a synthetic image dataset using both a classical approach and a quantum approach. With a classical approach, we provide this input noise vector by generating random numbers with our computer. But actually, random numbers generated by a computer are not really random. You can detect a pattern in them. So by providing a quantum input noise vector, those numbers should really be random. And so we would like to see if this can improve the generation or not. Then we want to develop a model in order to estimate crop yield. So, for example, similar to what was done by the chickens, we want to use object detection in order to detect the grapes in the vineyard, and so be able to count them and see how many are they and how they also their maturation state is. And we are going to prototype this on an edge AI device using the model for field application. So our goal is to be able to improve crop management and maximize also crop production while minimizing the use of fertilizer, pesticides, and water resources, for example. So this is the idea. If you're interested in something more about this project, feel free to contact me. You have my contacts at the end of the presentation, or also go through our social media and website, which are really well maintained, in which you can find more details about also the other parts of the project. Moving to the second one, here we are going to focus on weather, which is not directly used in this project for agriculture, but it is used for energy. But anyway, as I said, the weather is really important also for agricultural models. So in this project, we want to translate weather information into something that can be meaningful for the energy sector and the infrastructure it relies on. And the areas of work here are also 5. In the first one, we created the environment for weather modeling and climate projection. Then we develop a blended weather model, which is the classifier-based one that I used to give the title to this presentation, in which we only created a weather model, so there is no energy involved. Then in this project, we would like to translate this meteorological information into energetics and also model the infrastructure that may be damaged by phenomena like slow landslides. Here, the partners of the project are mainly industrial rather than academic. And as I said, I will focus on this classifier-based model as a second area of work. First of all, before diving into the classifier, I would like to introduce a little bit what is weather forecasting, so that we are all on the same page. So first of all, the question that we need to answer is, how do you forecast the weather? So the dominant approach is to use numerical weather prediction models. Here you see an example of a simulation for wind speed over Europe. These models basically solve mathematical equations that are based on physics in order to explain how air masses move and also how heat and moisture are exchanged in the atmosphere. And they are initialized with the present atmospheric conditions to predict the future. So we know how we can forecast the weather, but we can also describe how the weather was in the past. And to do this, we rely on reanalysis, which is a product generating by combining numerical forecast models, observation, and physical laws. And at the moment, reanalysis are the best estimate of the past states of the Earth system, since they provide a high resolution information of past weather events. So what is the link between AI and HPC and weather? The link basically started 2 years ago, because in the past 2 years, the world of weather forecasting has been completely revolutionized by AI. Here you see a timeline of some models that have been developed by major tech company, but it could also go on. And for example, last week, I think Microsoft released another model. So what happened is that large tech companies have begun to develop predictive weather models by basically using their expertise in artificial intelligence and the vast amounts of data that are available from reanalysis since the 80s, which are freely available. So you put together expertise and data and you get very good AI models, as you know, probably. So the result was that the models that these tech companies developed had an accuracy comparable or even better to the classical models, with a greatly reduced computational time once trained. Indeed, you can infer this model in a matter of seconds. So in 2 years, from 2022, it was possible to obtain models that had an accuracy that took more than 40 years of research and work to obtain. And this is really a game changer for this kind of field. So what we decided to do was not to create a fully AI-based weather forecast model, but we wanted to develop a short-term weather forecast model that exploits numerical simulation models that already exist in order to provide an improved forecast at each grid point and for each forecast hour. So our approach was to, first of all, select the numerical models that we wanted to use and a reference for model comparison that can be area analysis or weather station data. We decided to use area analysis after validating it against weather station data. Then we selected our variable of interest that can be temperature, radiation, wind, but they can also be, for example, precipitation, which are important for agriculture. And we developed a methodology to obtain the best forecast by solving a pixel-wise classification problem. And finally, we evaluated the new model forecast capabilities with respect to the starting numerical models. So I want to spend a few words about what pixel-wise classification is. So when you're working with computer vision, you can have an image, for example, and if you train a model to detect if a cat is in the image or not, that is a classification task. You can also localize the cat. So this is a localization or object detection problem. If you want to do pixel-wise classification, you, for example, create a semantic segmentation model that can associate to each pixel of the model, of the image, sorry, a class. So it will populate the image with zeros, for example, in every pixel in which you have the cat, which is here colored in yellow. It will put 1 in all the pixels in which you have a grass, and so on. So what we want to do is to use this approach to select the best model. So for each pixel of each image, which for us is 1 hour of prediction, we want to select which model is closest to the reference. That for us is reality and the reanalysis. So what we did was to take 2 models. Here, for example, I'm going to show you the process and the results for the temperature. You get the temperature from model 0 and from model 1. This is 1 hour of forecast of both models. You stack them together, one onto the other, basically, and you give it to a neural network model. We decided to use a UNet classifier because it is really good in solving semantic segmentation tasks, but we are aware that there are also other models, other architectures that can be used, but this was the first try that we did in this area, and we are actually not aware of other works going on trying to do this, so we were satisfied with this choice. And what you get in output once the model is trained is an output probability map. So in each pixel you have a value between 0 and 1, which is the probability of it to that pixel to be associated with model 0 or model 1. And by post-processing it, you are able to get a map in which you have only zeros and ones. So in this case, all the black pixels are model 0, which is giving the best prediction. And instead, all the white pixels are model 1. So one challenging thing was to get a forecast model that had an historical database and also area analysis, and these things had to overlap. So we were able to get the 2 models and the reanalysis overlapping from 2017 and 2021. So we used 3 years for training, 1 year for validation, and 1 year for test. And we trained this model on the Leonardo supercomputer in Bologna using 1 node with 4 GPUs, and the training took about 9 hours. Once trained, we had to perform a double comparison. So the first comparison evaluation was about the classifier performance in selecting the correct model. And the second one instead was the performance of the new model with respect to 2 individual models that we used as input. So about the first comparison, here, for example, you have for 1 hour of forecast, the model labels on the left and the model prediction instead on the right. So we evaluated it on our test set, and we got an 82% accuracy, which is pretty good. It means that we are classifying 18% of the pixel throughout our entire test set. And we also wanted to check class imbalance. So use precision, recall, and F1 score, which are metrics to say if you are always misclassifying towards one class or the other and the type of error you are doing. And we see that there is a good balance. They are both around 80%. And so we were overall we were satisfied with this solution, even though we are aware that there are other architectures out there that may be providing better results, but at the moment, this is a pretty good solution. In terms of model performance, we decided to evaluate in different ways. Here I propose visual evaluation in order not to provide too many numbers. So on the left-hand side, you have the bias. This is the average bias for each pixel on the entire test set. So on the left-hand side, you have model 0, in the middle, model 1, and our classifier on the right. So you can see that for model 0, about temperature, it is slightly overestimating temperature, while the model 1 instead, it is slightly underestimating it. And our classifier has a map that is much whiter, and it means that it is much closer to 0 in terms of bias with respect to the other models. So we can say that from these and also other metrics that we calculate, that our classifiers outperforms individual model prediction. So this is a satisfying solution, and we are happy with that. And what you need to keep in mind is that weather forecasts are also an important input for various agricultural models. So you can, if you have a improved weather forecast, you can also use it as input for several agricultural applications. So with this, I end my presentation. I hope it was interesting for you. I thank you for your time. I am available for questions now, and even if you want to contact me later, here you have my email, and you can also go on our social media and the website that are really well maintained and are always updated with new information. So thank you very much.
Meanwhile, we will welcome our last speaker. So with us, Professor Dr. Janez Perš, an associate professor at the Laboratory of Machine Intelligence and Faculty of Electrical Engineering in Ljubljana, and also expert in machine vision with a wide range of research interests, including embedded and distributed systems, robot vision and sensing of autonomous systems. So today he will talk about how applying HPC and AI in agriculture, specifically for close range monitoring of tomato crops for growing optimization. So Janez, let's start.
Thank you. So I hope you see everything. Can you hear me? Right? Okay, good. So first of all, I will talk about work that has been helped and done by many people. So some of them are here. And of course, we have been supported by University of Ljubljana and the Lush company, which is the company that actually grows those tomatoes. Now, I will shortly show the actual tomato production in Lush. Then I will talk a bit about AI in agriculture, and most importantly, how does it map to HPC? Okay, because during our work, I came to very interesting conclusions that are maybe not very obvious, as maybe you heard it from my question before. So then I will show you two examples of applying AI to, let's say, early stage research, but in terms of, let's say, working prototypes and so, but actually promising results for certain tasks that need to be done. So we're talking about Lush, which operates huge greenhouses. These are their PR images, I think. But you look at the left one, and you will see actually how huge this thing is. I think they have 15 kilometers of actually tomato plants put there. So even to walk through it takes hours for a human. So this is huge potential for optimization. Now, these greenhouses are heated, temperature controlled, let's say, and they are highly optimized, but they are not hydroponic. So they use substrate to grow tomatoes, which has important consequences for what kind of automation they really desire. So if we look at these plants in that actual greenhouse, the idea is, of course, rapid growth, because you have all conditions, shorter time to maturity. You have basically you're little weather dependent. You know what they do is they change different kind of crops. You know, so they produce the tomatoes almost all year. It's very space efficient, and they have very low use of pesticides. I think they don't even use them. I'm maybe not correct. At least not in normal production, unless there is like some kind of outbreak of a disease. So challenges here are, of course, picking. Everybody talks about picking, but here it is done manually, because their products are ripe tomatoes. So this is different from hydroponic plants in Netherlands. As you know, everybody knows about these. They ship green tomatoes all over Europe, maybe all over the world. They actually produce manual soft ripe tomatoes, and those need to be picked by hand. What is the problem here or challenge is yield estimation, crop yield estimation, prediction of harvest time, and of course, rapid detection of disease. And these are importantly critical for greenhouse economics, because crop prediction, yield prediction, actually helps you to to sell your produce in advance. And you have you can actually, because you do it in advance, you can have very good prices from the producers. Kind of much better if you need to sell, you know, tons of tomatoes that are ripe from today to tomorrow. So supervision, it's one of the things they're interesting in here. Now, of course, the other thing is detection of anomalies like pests and disease. And what you see on the left is the first prototype done by our lab and robotics lab at Faculty of Electrical Engineering. And this was basically something that has turned out to be a bit too advanced. But what you see here is the whole greenhouse is covered with these, let's say, tracks, but they're used as a tracks for their own trolleys, even when they manually harvest, examine things, and also those are heating pipes for heating in the winter. So basically, two important things are harvest prediction, like amount, time, and early detection of any pests or disease. Now, now, obvious sensing modalities that you can use for this are color camera, which can be used to determine fruit size, ripeness, and of course, the detection of anomalies like the leaves that are getting dry, or you know, the any kind of disease that actually reduces the yield. Now, of course, there is also a depth sensor in both of our prototypes, because if you want to actually determine very good, let's say, accurately yield, you need to know the physical size of the object, not the apparent size of the object that you get it in the images. Yeah, so you need to know that if this big tomato that you're seeing is close and it's big because it's close, or it's really big because it's massive. Yeah. So for accuracy, you would need depth. Now, there are also some not so obvious sensing modalities, and I would really like to emphasize that this, what you see, is prototype again, second prototype, and third one is in the works. So this is, let's say, poor man's multispectral camera, which has an advantage over normal RGB camera, by having better spectral sensitivity. Yeah? So because it is known that some anomalies are visible when in some of the spectral bands, Multispectral cameras are usually quite expensive, and this is kind of an attempt to make inexpensive implementation with rotating filter. This is one of the implementation that is actually being considered, in the multispectral camera technology, but it brings some problem, as you will see later. So what you see here is Intel RealSense, which provides RGB image, so this means color image and depth for each pixel. And then you see here on the top is basically another camera, which is near infrared and RGB, and actually the different filters are rotating in front of it, so you can acquire multispectral images. So yeah, this is a prototype. Now, what can we get? This gets interesting. So what can we get from this image, from this multispectral camera? You see here the spectral response of our filters, and on the right side you can see actual images in, let's say, as shown in RGB. Yeah, so we have near infrared, which actually looks, of course, gray. And then we have special near infrared, which should emphasize the water content. Yeah, so it's very narrow band, around 975 nanometers, and then we have also near ultraviolet, and then you have deep red and bright red, and three kinds of green, and then blue, and so on. So it's still a research. Now, this is our acquisition hardware, and now we will talk about how does AI for agriculture maps onto the high performance computing. So if you have your data, like you've seen here, yeah, you can then process this data in multiple ways. And first approach is inexpensive embedded systems just for inference. There will be just NVIDIA Jetson, Xavier, various specialized solutions that can be bought as for about 20 or 30 euros. Now, the problem with those are they support very limited amount of algorithms, very, let's say, shallow networks, and so on. So then the second option is, of course, PC and gaming cards. These are also popular in research. Let's say majority of our lab on training the models is done on these things, not actually supercomputing. We are moving towards supercomputing, but not at the pace I would like to. So yeah, the third way is actually going to supercomputer and use what you have there. Now, in the embedded variant, so the first thing is fast inference, simple algorithms, real-time application. For gaming hardware, you have also reasonably fast inference, demanding algorithms, which can also run quite fast, and but they're not like real-time, okay? And then you have supercomputer, which is, on one hand, of course, processes things fast because you have usually state-of-the-art GPUs, data center GPUs there. But end-to-end, it has quite high latency because you have job queuing, yeah? And job queuing is something which our researchers hate, okay? So now, to make things better, agriculture often includes slow processes, okay? I always felt sad for the people like doing PhDs in this field, and they had to finish them. It was for a while ago in like 3 years. For 3 years you have 2 crops, and then it's the end of your PhD. So dynamics here is actually pretty slow, much slower than usual in AI. So plants need time to grow, and if you have major challenges like growth, yield, harvest, this is especially slow. Now, even disease and pest response is like, if you say, oh, we need to respond in real time, has a really, really soft constraints, okay? So you see that there is somewhere some kind of organism, the pest, but you don't need to attack this in a millisecond, yeah? 1 hour will be probably okay, or maybe 1 day will be okay. So there is, as I think, the things that I came in contact with, little need for low latency systems, as understood in AI, yeah? Because you have your vineyard, it will be still there tomorrow, yeah? So quality of the results can be put above all other requirements, because often in these things, as you have here, multiple approaches, we always have a trade-off. Yeah, you can have embedded system, very fast, real time, but only very basic algorithms can run there. So in agriculture, you can go to HPC and process data, queue the data, and you'll be still fast enough. Now, I will continue with two examples of our own work. One is tomato segmentation, and the other is multispectral to color image alignment. Okay, and let's look what these are about. So tomato segmentation is absolutely a basic task, like let's say fruit segmentation. If you want to estimate the yield, if you want to estimate the harvest time, you know, and all of these things, except for plant disease, tomatoes or fruit are the thing to go. And the result of tomato segmentation, what do we want, what do we need, is that we get from pixels on screen, we get all the pixels that represent tomatoes. Because then we can go on, when we have this, we solved a lot of problems, and then we can go towards estimating the size of the fruit, estimating the distance of the fruit, you know, estimating the weight of the fruits, and so this is one of the basic steps. Now, in detection of pests or disease, sometimes multispectral images are also important, but we need to align them, yeah, to other modalities, and this is especially regarding the depth, yeah, because okay, you have tomato, you know that this tomato is let's say green in color, yeah, and then you want to look at it, maybe is there a sign of some pest or some disease, same for plants and so on. So if you want to actually connect these two modalities, we call them modalities, you need to actually make connection between the pixels. And now what we did in our lab, of course, was the new model for segmentation of tomatoes. Now, I won't go into details. This is just a nice picture. So it's nice, let's say, sciencey here. But this model is diffusion model. I don't know if you know about what diffusion models are, but the main idea is shown below. So you start with the noise, okay? And then you basically train your model to actually get take the noise in and generates an image. Okay, so any diffusion models are slow. And what I actually remembered here, but because this approach is good, it was also awarded the best practical award in the conference. It is so slow that my PhD student, our PhD student who worked with it says, okay, yeah, don't say too much about it. It won't be used for a long time because it's so slow. And of course you need real time. No. Okay. So let's look at it's better in some aspect. You see, we also had our own data set from Lush, so we really tested it out. So it's an example of the better algorithm as those who are there. And now, of course, let's look at how the HPC comes here in. So it's the diffusion model. It's slow. Let's forget it. It's slow. Cannot optimize to the hilt. No more way to do it. It's already parallelized. It's already running on GPU. So how can you use supercomputer? Well, let's go back. If you go to this Lush greenhouse, they have 15 kilometers of plants. So you need hours just to walk through. So the idea is now to, of course, that's I put this our first prototype robot here, to actually automatically record the whole area, all 15 kilometers. When do you do it? Maybe through the night. Yeah. Then you're uploading this data, and then you take your time and process all of this stuff, because nobody will be interested in yield, crop yield prediction in 3 a.m. in the morning, right? if you deliver this at noon next day, it will still fine. So you can actually use the, let's say, awesome parallelism of the supercomputer to process, let's say, 1 image per every meter of your crop. And this would be amazing. Yeah. So this is the idea here. Now, another approach I want to show, I want to go into these details, is when we're doing this into agriculture, we often actually come to the need to have multi-sensor system or multi-camera system, we show here multi-spectral system, but in all these cases, we need to join information from multiple cameras. And here we have the problem of parallax. What is the parallax? If you move, yeah, let's say you see the objects that are close to you are, let's say, virtually moving faster. The objects far from you are moving slower. Yeah. So, and if you have 2 cameras at certain distance, then this is called parallax, and they won't see the same image. So here are some examples from multi-camera alignment. We have this. Well, these are examples that from other area of work. This is autonomous boats, robotic boats. But here you can see different modalities like RGB image, and then you have polarization camera, and there is LiDAR shown here, and near infrared, and the other near infrared, and so on. So this is field of research that actually it's not very, let's say, it's not a very grateful field of research, but you really need it. So what we had is our input data from the same greenhouse, multiple spectral channels, as I showed them before, and RGB image, and then depth. You see lower right, it's depth image, just shown in a way of the color scale. So you need depth to actually solve the parallax, because you have to check, okay, this thing is so far, so to counter the parallax, you have to calculate, I need to move certain pixels for that amount, yeah? So what we did is first we went the easy way, find the good points to align. It's called super points algorithm. Then you super points using super glue. You can find about it, you can ask me about 2 algorithms, but the problem is that this cannot solve your problem as soon as you have 2 cameras. Okay, so you have 2 cameras, they will get a slightly different angle of your crop if you are close by. And in the greenhouses, you will be always close by unless there is really non-optimal greenhouse. So then let's go back to these other examples from autonomous boat. So what we see here is basically the thermal camera, like heat camera, yeah, far infrared camera mapped to RGB, that means color image. What you can see here, it's actually like this wavy edge, because correction of parallax requires actually let's say non-linear transformation of pixels. So each pixel have to be recalculated to see where does it fit, depending on depth. And this cannot be pre-calculated. So what we did here, we transformed this RGB, that means color depth image, to the point cloud, yeah? And then we aligned the point cloud to spectral channels, and we got the image as you see here. Now, what's the problem here? Once you show your point cloud, because now you're looking at the point cloud, there are some points missing because they simply, there wasn't any point there to provide us with the information. And you have an image that is all wavy, and because you have parallax, you also have places, which cannot be aligned with other image, because, as you move from one to the other camera, you looked at something that is now whole, yeah? So, of course, we need more processing here, and this is ray tracing, where we go from the camera, shoot a ray out, then try to find the closest point in this color point cloud of our scene, yeah, imagine, and then trace it back, and this way we do nearest neighbor interpolation, with results is, you look at the image now, as I change it, looks in this different image. So this image is also not perfect, but I'm pretty sure that these webs here that appear due to this artifact, would mess up with any kind of a deep algorithm for other tasks like that we are working on now, that's crop estimation and things like that. So you need this, as a first step. So none of these steps can be pre-calculated, and this ray tracing I was talking about was actually done on Arnes supercomputer, because none of the PCs that we have in our lab were fast enough for my master student to finish his work in, let's say, allotted time. So this is actually the problem. So my final thoughts. If you're talking about crop yield prediction or anomaly detection, these, considering other other AI fields like autonomous driving, these are really forgiving here. Autonomous driving, you have to react in a hundredth of a second or you kill a person. Here, you detect that something is rotting. It could rot for 2 more hours. Probably it won't be that bad. So actually, agriculture, many tasks are compatible with supercomputing architecture. And I would really like people to think about this, because if you have reasonable queuing, and queuing is something that AI researchers hate, because they prevent them from cycling very fast through their ideas. Reasonable queuing is still fast enough for, let's say, real-time constraints in many of the agricultural tasks, because plants grow so slowly. So of course you have fast GPUs. Massive parallelism can be quite nicely used. So yeah, you have the method that cannot be parallelized on particular image. Okay, but why do you use supercomputer? Because so you present your whole greenhouse, like 15,000 of images that you captured by your robot going through it. So my advice would be you should always focus on the high quality results, even if it costs intensive computation, because the real-time constraints here are in those things like crop prediction are not very strict, and they're quite very compatible to HPCs. So this is everything from my side. Thank you.
Thank you, Janez, very much. Any questions? Okay. So if there are no questions at this point, still you can reach us out at www.slink.si, so NCC Slink website. You can drop us there an email, and we will take care to provide your request to the speakers. So thank you very much to all presenters. It was actually a great insight into what technology can do and how can support agriculture. It's very important for us for growing our own food and making the sustainability of our agricultural land. And at this point, I would say thank you all the visitors. Hopefully to see you soon in our next events, and take care. So bye.
Bye.
Bye.